Bristol made the most successful sleeve valve aviation engines from the 1930s leading up to World War II and well into the 1950s, and were competitive even against the best poppet valve radials of the time. It was claimed that sleeve valve engines improved on poppet valve engines in several ways, most notably by allowing higher compression ratios, which meant more power and better fuel efficiency. But with the benefit of hindsight, many have suggested that it may not have been the best use of resources to develop an entirely new valve technology with war looming on the horizon. Before we get into it, I'm assuming some may not know what sleeve valves are, so here's a quick overview. Traditional internal combustion engines use poppet valves to control the intake and exhaust of gases. In a radial engine, the poppet valve system consists of valve springs, guides, rocker arms, push rods, a cam ring, and the valves themselves. The sleeve valve does the same job, but in a different way. Inside the cylinder sits a sleeve, a tube with a series of ports cut into it for intake and exhaust. As the sleeve moves, those ports align with passages in the cylinder wall, letting exhaust gases out and drawing fresh air in. The piston runs inside the sleeve. The sleeve moves up and down with an oscillating back and forth rotation to open and close the right ports at the right moment. The sleeves are driven by gears, typically from the front of the engine. So why deviate from trusty poppet valves? By the 1920s, it was a well-proven design, even though it had some drawbacks. The most important advantage claimed for the sleeve valve was the ability to run higher compression ratios. The hot exhaust valve head in a poppet valve engine is a hotspot that can trigger detonation or pre-ignition before the spark plug fires, which limits how far you can push compression ratio. Remove the valve, remove the problem. Now, as fuel octane ratings were increased over time, that advantage narrowed. But not immediately, as the main octane boosting additive corroded poppet valves. Before we dive into that, we need some context on Bristol's sleeve valve development and achievements to lay any remaining doubts about its success to rest. The sleeve valve was designed by Charles Yale Knight in 1903. Knight was reportedly frustrated by the clattering of poppet valves in his car, and this led him to design the sleeve valve mechanism. It proved a popular alternative in early luxury cars, where quiet running was a selling point. While Knight's sleeve valve came first, it was the Burt McCollum single sleeve design that ultimately survived and was refined for aviation use. The main difference was the Knight used two concentric sleeves and the Burt McCollum used a single sleeve, which proved more practical. Two people were instrumental in bringing sleeve valves to Aero engines, Roy Fedden and Harry Ricardo. Around 1924, they began exploring the possibility of an air-cooled sleeve valve aircraft engine. Ricardo hypothesized that the hot exhaust valve was the main factor keeping detonation limits low. Early test engines strongly suggested that he was right. Their sleeve valve engine could sustain one full compression ratio higher than the same engine fitted with poppet valves. This was a significant and very promising result. Ricardo published several papers on the advantages of sleeve valve engines, which persuaded the British Air Ministry to fund a development program. They decided that Roy Fedden at Bristol was the man for the job, and work began in 1926. Development was far from smooth, but by 1931 their test engine, an air-cooled V-twin, passed a 100-hour endurance run at a respectable 2000 RPM. Fedden then applied the sleeve valve design to a radial engine, and in 1932 the Bristol Perseus made its first run, and thus became the first production sleeve valve Aero engine. The Perseus made its first flight in 1933, powering a Bristol Bulldog. Bristol publicly made a very big deal about the engine's success, touting its smooth running, reduced parts count, and freedom from poppet valve problems like broken valve springs, valve float, and had near zero maintenance requirements. The Perseus had a 300-hour TBO, very good for the time, and the outlook for the sleeve valve engine looked genuinely promising. There was, however, a significant manufacturing problem. The sleeves were hand-finished and required individual matching of pistons and cylinders. The engines were extremely sensitive to sleeve out-of-roundness. Deviation needed to stay below 0.0002 inches, and early mass production efforts tended to produce sleeves that were not perfectly round on that scale. Bristol eventually solved this through centrifugal casting and other manufacturing innovations, though it's worth noting that mass production was only fully achieved by 1938. The Perseus powered several types, including the Blackburn Botha, Rock and Skua, as well as the Westland Lysander Mark II. The Perseus Mark XII was a single-row, air-cooled, 9-cylinder radial producing 830 horsepower at 2,650 rpm on takeoff, from 24 liters of displacement, with a dry weight of 465 kilograms. It had a single-speed supercharger, a compression ratio of 6.75 to 1 on 87-octane fuel, a propeller speed reduction ratio of 0.5 to 1, and a specific fuel consumption of 0.43 pounds per horsepower hour. Design work on the successor to the Perseus began as early as 1934, and it became Bristol's most successful sleeve valve engine, the Hercules, with over 57,000 eventually built. The Hercules was a double-row, 14-cylinder, air-cooled radial displacing 38.7 liters and weighing 875 kilograms. The Hercules II produced 1,272 horsepower at 2,800 rpm for takeoff, with a compression ratio of 7 to 1 on 87-octane fuel, a reduction ratio of 0.44 to 1, and specific fuel consumption of 0.43 pounds per horsepower hour. Like the Perseus, it retained a single-stage, single-speed supercharger. It passed its 100-hour type test in early 1937, but the Hercules experienced significant crankshaft torsional vibration. This was addressed by the installation of a Salomon damper. The Hercules entered service in mid-1939 and went on to power many aircraft, most notably the short Stirling, the Handley Page Halifax from the Mark III onward, the Aero Lancaster Mark II, and the highly successful Bristol Beaufighter. Its most powerful variant exceeded 2,000 horsepower. The engine also had a solid post-war life in transport aircraft like the Bristol Freighter, Vickers Varsity, and Handley Page Hastings before turbojets and turboprops took over. On the freighter, the Hercules' TBO was reportedly eventually increased to over 3,500 hours. I need to mention that wartime TBOs would have been significantly less. The Hercules was Bristol's most successful sleeve valve engine, but their most powerful was the Centaurus. Design work began in mid-1937 and it passed its type test in early 1940. With 18 cylinders in 2 rows of 9, it displaced 53.6 liters. The Centaurus Mark VII produced 2,520 horsepower at 2,700 rpm on 130 octane fuel with a compression ratio of 7.2 to 1, a gear reduction ratio of 0.444 to 1, and a dry weight of 1,222 kilograms. Specific fuel consumption was around 0.48 pounds per horsepower hour, and specific oil consumption in cruise was 0.008 pounds per horsepower hour. It had a single-stage, 2-speed supercharger which improved performance across a range of altitudes, though the absence of a 2-stage supercharger always limited its high-altitude capability. More on that later. The Centaurus entered service too late to play a major role in the war, but went on to post-war fame in the Hawker Sea Fury, which served with the Fleet Air Arm well into the 1950s. Before we get into what the sleeve valve was claimed to achieve, let's take a closer look at how it works. We've already covered that the sleeves combine an up and down motion with an oscillating rotation. But what actually creates that movement? The sleeves are driven from the front of the engine by a set of gears connected to the crankshaft. If you've seen a photo of this gear arrangement, it can look quite intimidating, but it's not significantly more complicated than a poppet valve drive system when you compare the two complete systems. These gears drive a ball crank mechanism which translates the rotational input into the sleeve's combined reciprocating and oscillating motion. When the ports in the sleeve align with the passages in the cylinder wall, the cylinder could either draw in fresh air or expel spent gases. In operation, each sleeve has 3 ports used for intake and 2 for exhaust, but only 4 physical ports in total. One slightly differently shaped port does double duty, serving as both an intake and exhaust port depending on where it is in the cycle. The exhaust passages are located at the front of the cylinders and the intake passages at the rear. To show exactly how the ports open and close, I've created a moving 2D animation based on period sketches. These are the dedicated intake ports in the sleeve and their corresponding passages in the cylinder wall. These are the dedicated exhaust ports and passages. And this is the sleeve port that serves double duty as both intake and exhaust. Starting with the piston at top dead center, the beginning of the intake stroke, the piston descends and the dedicated intake ports and the shared port open to draw in fresh air. This is the fully open position. The sleeve then closes all ports as the piston rises through compression and remains closed through the combustion stroke as the piston descends again. From bottom dead center, the piston rises on the exhaust stroke, and the dedicated exhaust ports and the shared port open to expel the spent gases. At top dead center, the cycle begins again. If you enjoy these videos, please consider supporting me on Patreon. Links in the description, and members get some nice perks. Back to it. Harry Ricardo outlined 6 specific advantages he believed the sleeve valve held over the poppet valve, and we're going to work through each one and see how they hold up. With the history clearly illustrating the success of Bristol's sleeve valve engines, surely it made good on its claims. Well, it's actually a bit more complicated than that. Ricardo's first claim was that without poppet valves in the cylinder head, the spark plug could be placed at the center of the combustion chamber, meaning the flame travels an equal distance outward in all directions. That's correct, though the immediate question is, don't Aero engines use 2 spark plugs per cylinder? Ignition is a redundant system on Aero engines after all. The answer is yes, but that doesn't make this claim invalid. You can fit 2 spark plugs between poppet valves, but there's virtually no freedom to place them where you actually want them. Without valves taking up space, designers have far more flexibility. What Bristol ended up doing was placing both plugs close together near the center of the head, something virtually impossible with poppet valves in the way. So this claim holds up, even if, in my opinion, the practical advantage is relatively modest. Ricardo's next claim was that the exhaust valve was the weak link, especially in low compression ratio engines, which in the 1920s was virtually all engines. Lower compression ratio engines have higher exhaust temperatures. The more a charge is compressed, the more it can expand during combustion. A higher compression ratio means a higher expansion ratio, and the more the gases expand, the more of that combustion energy gets converted into useful work and less goes to waste as heat. Low compression ratio engines do the opposite. Less expansion means more energy wasted as heat, and the exhaust valve is exposed to all that heat. This was a real problem at the time, but we have to remember that 87-octane fuel arrived around the late 1920s, and 100-octane was introduced in Britain by 1939. Thanks to this, by the time sleeve valve engines were in production, poppet valve engines could run at higher compression ratios, and with that, their exhaust temperatures came down considerably. So while this claim was valid and important when Ricardo first made it, the exhaust valve temperature problem had been significantly reduced by the time war broke out. Ricardo's next claim was that the absence of a highly heated exhaust valve head reduced the tendency towards detonation and pre-ignition. There's a subtle but important difference from the previous claim. Claim number 2 was about the hot exhaust gases making the valve the structural weak link. This one is specifically about the hot valve surface acting as a hotspot that triggers detonation, limiting how far you can push compression ratio. For the very low compression ratio engines of the 1920s, this was a real and valid concern. But as higher octane fuel became available, compression ratio was increased and exhaust temperature dropped, reducing valve head temperatures. And poppet valves themselves improved enormously between 1920 and 1940. Metallurgical advances and design changes improved exhaust valve cooling considerably, most notably through hollow stems filled with sodium. However, how fuel octane was primarily increased was by adding tetraethyl lead, which caused corrosion issues with poppet valves. But this problem was eventually solved with corrosion-resistant coatings. But there's something else worth acknowledging. If hot internal surfaces were truly the main limiting factor for compression ratio, sleeve valve engines should not have had much of an advantage. The sleeve itself, coated in a thin oil film, acts as a thermal barrier, slightly increasing internal surface temperatures, particularly at the piston, which in a sleeve valve engine was reportedly as much as 50 degrees Celsius hotter, as vaguely stated by Fedden. Experiments with externally cooled exhaust valves have shown barely any benefit towards increasing compression ratio, at least at rich mixtures where maximum power is produced. There's an argument to be made that hot surfaces weren't the primary limiting factor for compression ratio, at least not once high-octane fuel was available. I'll list some sources in the video description, as I know there may be pushback on this. But then how did sleeve valve engines consistently achieve around 1 full compression ratio higher when it was introduced? That is not theoretical, it was actually achieved. So what was really going on? The fourth claimed advantage was that the sleeve intake port opened directly into the cylinder, creating beneficial turbulence, or more precisely, swirl. The sleeve valve had an inherent ability to generate swirl in the incoming charge, and crucially, it also offered control over the swirl rate, which matters because too much swirl is also undesirable. Swirl is rotational motion in the cylinder, the air spinning as it enters, and it has a very positive effect on raising the detonation limit. After the spark, the flame front travels outward from the ignition point. The unburnt mixture ahead of it, called the end gas, gets heated as the flame approaches. If the end gas reaches its auto-ignition temperature before the flame front arrives, it detonates spontaneously. That's unplanned, unpredictable, and causes engine damage because this is not a relatively slow-moving flame front like in normal combustion, but quick mini explosions. Swirl raises the detonation limit in 2 ways. First, it improves mixing of air and fuel, increasing homogeneity. Without swirl, the mixture can be uneven, with richer and leaner pockets. These inconsistencies can create local hotspots prone to early detonation. Better mixing reduces this tendency. Second, swirl increases the speed of the flame front by adding air motion to it. The faster the flame travels, the less time the end gas has to auto-ignite. It's exposed to high pressure for a shorter period. Together, these two effects reduce cycle-to-cycle variation in peak combustion pressure, meaning detonation becomes more predictable, and the engine can safely run closer to the detonation limit. Interestingly, Ricardo never directly attributed the compression ratio advantage to swirl in his published work, at least not that I could find. Today, the benefits of swirl are well understood, and it's now widely considered to have been the most significant factor behind the sleeve valve's higher detonation limits. The next claim was that the breathing capacity of the sleeve valve engine should be at least equal to the best poppet valve arrangement. What's interesting is Ricardo didn't claim it would be much better, but barely equal. I think I know why he was restrained here. With a poppet intake valve, even when fully open, the valve itself sits in the airflow and restricts it. The sleeve valve has no such obstruction, only ports in the sleeve for air to enter and exit. And in theory, you could make those ports larger or more numerous to improve airflow further. But there's a structural limit. The larger the ports, the thicker the sleeve must be made to avoid deformation under the enormous pressures of combustion. If the sleeve distorts even slightly, there's a risk that the piston rings sliding across these port openings can momentarily catch on the edge of a port with destructive results. The obvious solution is to make the sleeves thicker, but that adds weight and increases the parasitic load the sleeves place on the engine, which is equally unwanted. So there was a careful balance to strike: ports not too large, sleeves not too thick. My interpretation is that Ricardo understood this constraint very early on, which is why he didn't claim much superior breathing capacity. The final claim was that sleeve valve engines would be more compact with a smaller frontal area. Without poppet valves and all their associated hardware in the cylinder head, the cylinders could be shorter, and on a radial engine, shorter cylinders means a smaller cross-section and less drag. However, the portion of the sleeve containing the ports needs to be clear of the combustion chamber during compression and combustion. It does this by sliding up into the cylinder head into a space called the junk head. And as you can clearly see in these photos, these grooves extend well above the top of the cylinder head. That space takes up most, if not all, of the room that the poppet valve system would have occupied anyway. A full cross-section comparison is more nuanced though, as there are many things to take into account. The bottom line is the smaller frontal area wasn't realized in any meaningful way. This view is supported by Roy Fedden, who echoed all of Ricardo's other sleeve valve claims, but conspicuously left this one off his own list. When you compare radial engines of roughly equal power, some sleeve valve engines had smaller cross-sections and some had larger ones. Any size difference came down to other design choices and trade-offs, not only the valve system itself. Ricardo also listed two disadvantages of the sleeve valve engine. The first was the additional thermal barrier created by the sleeve and its surrounding oil film. Early tests suggested that sleeve valve pistons ran cooler than its poppet valve equivalent. But Roy Fedden, after leaving Bristol, stated that sleeve valve pistons ran some 50 degrees Celsius hotter. A hotter sleeve means more heat is transferred to the incoming charge during induction, which reduces its density and hurts volumetric efficiency. The second was the additional friction of the sleeve drive system. The concern was the large contact surface between the sleeve and cylinder, plus the piston running inside the moving sleeve. Ricardo eventually concluded the sleeve valve system had no more friction than a poppet valve system, a result that apparently surprised him. Fedden didn't raise friction as a concern in his paper, which I take as further confirmation that there wasn't a meaningful difference in practice. Beyond Ricardo's listed disadvantages, weight, cooling and oil consumption are worth addressing too. Sleeve valve engines were heavier for a given displacement than comparable poppet valve engines, meaning they needed to extract more power from that displacement to remain competitive. This they largely achieved through higher compression ratios. As for power to weight ratio, the picture changed significantly between the pre-war and post-war years, and by the latter period in the air transport service, Bristol sleeve valve engines were competitive. The other disadvantage was cooling the cylinder head, which was also more difficult. The actual head surface sits recessed well into the junk head, making it hard to reach with airflow. The early solution was dedicated ducting to redirect incoming air to these recessed areas, which was effective but added complexity and weight. Later designs addressed this with raised, finned cylinder heads, but that brought its own weight penalty. Finally, there are persistent claims that sleeve valve engines had high oil consumption due to oil escaping through the sleeve ports. The contemporary view, however, was actually the opposite, that they used less oil than comparable poppet valve engines. The figures support this. It's very high by modern standards, but the Hercules showed a specific oil consumption of 0.008 pounds per horsepower hour in cruise, compared to around 0.015 for the Pratt & Whitney R2800. I've covered radial engine balance in detail in the video linked in the description, but let's do a quick recap and then we'll consider how the sleeves affect balance, as they do have significant mass. Radial engines have great primary balance, which is the balance relating to the momentum of the pistons and connecting rods. But they have relatively bad secondary balance. That's the imbalance caused by the tilting of the connecting rods, which means pistons accelerate slightly faster through the top half of their stroke than the bottom half. Some radials, notably the Pratt & Whitney R2800 and Wright R3350, use secondary order balancers spinning at twice engine speed to address this. The Bristol sleeve valve radials, including the Centaurus, didn't have these. Probably not because they didn't need them, but more likely because the sleeve valve gear train at the front of the engine left no room for them. But that is speculation on my part. It could also be because of the weight this would have added to the already heavy engines. But what about the sleeves themselves? They move up and down like pistons, so wouldn't they make the secondary balance worse? Actually, no, and here's why. A piston's motion is driven by a tilting connecting rod, which makes its movement slightly non-sinusoidal. That's what creates the secondary imbalance. The sleeves, however, are driven by a ball crank rather than a connecting rod, which gives them a perfectly sinusoidal motion, which creates no secondary order imbalance. And, same as the pistons, they do not create any unresolved primary imbalance. As for whether sleeve valve radials were actually smoother running in practice than poppet valve radials, my best guess is the difference, if any, would be marginal. So was all the development that went into the sleeve valve engine worth it? With the benefit of hindsight, it's hard to argue that it was. By Fedden's own estimation, it had cost them £2 million just to find a way to mass produce the sleeves. Other development costs excluded. The resources spent to arrive at a technology only marginally superior to poppet valves, at best, would almost certainly have been better directed at rather building more aircraft with proven technology. But in the early 1920s, nobody could have known that, and the poppet valve may just as well have been a total developmental dead end, like was thought at first. But even with high-octane fuel and poppet valve advancements, sleeve valve engines maintained a slight compression ratio advantage of roughly 0.3 higher. That is very marginal, and marginal advantages have to be weighed against real cost. A sleeve valve engine was considerably more expensive to produce than a poppet valve equivalent. The more damning issue, though, is what the lengthy sleeve valve development distracted Bristol from. High-altitude performance became a hard requirement by mid-war on both sides for strategic bombing, and the fighters needed to escort or intercept them. Two-stage supercharging was the key to getting there, and at Bristol so much time and engineering resources went into solving the sleeve manufacturing problems that supercharger development was neglected. The same story played out at Napier with the Sabre, a remarkable engine I covered in a dedicated video. Without a two-stage supercharger, which is essentially two superchargers working in series to maintain intake pressure up to higher altitudes, Sabre-powered aircraft were largely confined to low and medium altitude work. The Typhoon and Tempest were outstanding in that role, but they couldn't operate as high-altitude interceptors or bomber escorts. And neither could anything powered by the Hercules or Centaurus. There's also the question if Bristol truly believed in the superiority of the sleeve valve by the late 1930s, when high-octane fuel and sodium-filled exhaust valves disproportionately improved poppet valve engines, or whether they simply had no choice but to continue. Fedden pretty much confirmed the latter when he said that Bristol passed the point of no return in 1934 when they irrecoverably shifted to the sleeve valve mechanism on all their most powerful engines. I don't blame Fedden or Ricardo for developing the sleeve valve. Their engineering was genuinely brilliant, and the world would be slightly more boring without it. But what do you think? Let me know in the comments, and thanks for watching. See you in the next one.